Hello, this is a video about the LabVIEW project, LabVIEW and Arduino project for the EC10 class. And today I'm going to talk to you about this design of a um, sound visualization and localization. And so what I'm going to start off with is I'm going to first mention this user interface, and this is basically where the user is able to control and manipulate the sound as it comes through and use it to direct the servo motor in a certain way. Well, actually, the servo motor gets. Actually, I'll explain that later. Basically, the user interface is what allows the user to change the volume, treble, mid-tone, bass, and then they can also see the path that the file is being written out to, and also the waveform of the left and right channels both show up on this graph calibrator. So I'm going to start off by talking about um, actually first I'll talk about the calibration process. So what I did for the calibration is I just basically I went to the oscilloscope and found the RMS values, or determined the RMS values from a single tone, and then I took the ratio of those RMS values and I multiplied the channel that needed that ratio by the value. And so first I split up the channels and I put one of the channels into an array. I multiplied that array by 1.6 because that was the factor of the factor between the two RMS values. And then I basically merged the left and right channel together again. So now what I did then is I filtered the sounds into the bass, midtone, and treble properties. So the bass is about 20 to 80 hertz is what I found from research, and so I made this 20 to 80, and then the midtone I put it at 80 to 320, and then the treble I just put it from 320 to like 1,000 or whatever. So basically, to do that I split up the three. I split up the sound into three parts, and then I filtered them into the parts individually, and then I made all of it combine back together. So yeah, this is basically if it when it works, whatever, if one of these is off, then that part of the frequency won't be processed into the output. So that's how you can manipulate sound. That's how the user can manipulate sound, actually. Okay, then I'm going to talk about the triggered recording properties. So basically, the way this program is written is it only starts recording once it can detect sound above a specific threshold. In this case, the threshold turns out to be 0.1, and the threshold can vary. It's determined by how sensitive the microphone is. So basically, at the threshold 0.1, I start recording, or this starts recording, and then it doesn't really manipulate the sound or anything. But yeah, so the way this gets written out to a file is by this wave file that I create in the beginning, and I make the wave file and I put a certain sample rate, 44,000, and then I generate the sound file, which is what this thing is. This is where the path is shown, and then I also, see what I do. I write out the file here at the end of the program. So that is how the file is written out. The way I have the servo motor working is I split the left and right channel, and then I find the index of the maximum values in each of those channels. So the reason why I do that is because I want to find the time difference. And so the best way to do that, or at least as far as I know, is by finding the difference of the periods. So that involves finding a specific unique point in each of the graphs, and I figured the peak would be the best way to go about doing that, or the maximum. So then I find the time difference, and well, that's actually a difference in frequency, so in hertz. So then I divide it by the sample rate, and that's a time difference. But then I used an equation basically to get the angle to which the serial motor should be churning, and that's all here. And I turn it to degrees, and then I put that through the Visa Communication 5 port in order for it to communicate with the Arduino program. So judging by what I've described to you so far, this program should work when it runs, and it should start showing you graphs when there's enough sound for it to detect. And so let's make sure that's what happens. Alright, so as you saw, it starts to show waveforms when there's music played, not earlier. And even though the white kind of overrules the red there, you can see the red and white waveforms there, not currently, but while it was playing. And so if you looked closely, you would see that they're at the same peaks precisely, thus calibrated. Let's actually make sure that this generated file works here. So I'm going to record, going to run this. Alright, so now I'm going to go to this path right here. It's 809, 306, and then there it is. So now let me show you how this, if you pay attention to this red LED, you'll be able to see that when I snap my finger here, once I run the program, it will be able to basically turn itself towards me. So let me see, I'm going to press this run button here. Okay, come to me. Well, and then I stopped it, and it's going to go back to 0. So basically that's how the whole system works. And yeah, that's hopefully that was helpful.